Welcome back. In this video, we're going to go over section 9.5, which is about dividing square roots. So taking a look, the first kind that we'll see doesn't take any special properties. In this one, we're just going to simplify the radicals as we've done before. So, and then simplify further. So we have the square root of 32 divided by 8. 32, we will factor that as 16 times 2. And still that's divided by 8. The square root of 16 times the square root of 2. That's divided by 8. The square root of 16 here is 4. So we'll have 4 square roots of 2 divided by 8. There, the common factor of 4 is divided out, and that leaves the square root of 2 over 2. And that's the end of that. For the next one, we have 8 minus the square root of 40 over 10. So we're going to focus on simplifying the square root of 40. So the 40, we'll factor that as 4 times 10. Everything else I'm just recopying. So I know that can be tedious, but in order to be correct, that's what we have to do. So we'll have 8 minus root 4 root 10 all over 10. And then the root 4 will end up being a 2. So we'll have 8 minus 2 root 10 over 10. And here there's a common factor of 2 in the numerator and denominator. So let's factor that 2 out of the numerator. And then when we divide out that common factor of 2, we'll have 4 minus root 10 over 5. And that is the end of that. So the last section, we used a product property of radicals. We have a similar quotient property of radicals, and it goes like this. If a and b are non-negative real numbers and b is not 0, whenever you're dividing, you have to be worried about 0, then the square root of a over the square root of b is the same as the square root of a over b. Or looked at another way, the square root of a quotient is the same as the quotient of the square roots. All right, so then this kind of brings up a question that can occur. In the first example here, we have the square root of 48 divided by the square root of 108. So we can ask ourselves, is it better to simplify the square root of 48, simplify the square root of 108, and then divide? Or should we apply this property, put it all into the same radical, and then simplify? It's kind of a personal choice sometimes, but often I think it's easiest if you begin by putting it all under the same root sign and simplifying the fraction and then going from there. All right, so 48 and 108 are both divisible by 4 at least. Let's see what's good. It's usually good to take as big a bite as possible. Let me see about factoring 108. 108 looks like 36 times 3. And then 48 is 6 times 8. So 6 and 36 have a common factor of 6 at least. So this will be the square root of 8 over 6 times 3. And then it looks like we have another common factor of 2, which can be divided out. So dividing that out, we'll have 4 over root 9, 4 over 9 rather. And then simplifying that, that will be the square root of 4 over the square root of 9. And those simplify to be 2 over 3. All right, so here's one for you to try. Take a minute and simplify this square root of 12r cubed over the square root of 6r. So pause the video and then try this and then restart the video and see how you did. All right, so if we want to combine these roots, we'll have the square root of 12r cubed over 6r. And here the numbers 12 divided by 6 will give us a 2 in the numerator. Sorry about that, Zoom crashed once again. So we're going to have the square root of r squared times 2 or r square roots of 2. You can write that as the square root of 2 times r if you like. Okay, and that's the end of that. All right, here's more. For this one, again, I think it's nicest if you combine the radicals, the radicands into a single radicand, and then simplify the fraction, then go from there. So 50 divided by 128, there's a common factor of 2 there, which we can divide out. So that will give us 25 over 64. That's nice. Those two are perfect squares, right? So that's, I'm sure, not an accident. X cubed over x will give us an x squared in the numerator. Now we can separate that back into two roots. That will be the square root of 25x squared in the top and the square root of 64 in the bottom. The square root of 25x squared will be 5x, and the square root of 64 is 8. So we'll end up with 5x on 8. Okay, so that's pretty fun. This one's neat because there's two variables in it. So pause this one, pause the variable, pause the video, try this one yourself and restart the video and see how you did. All right, so we're going to make this into a single radical with underneath 162 x to the 10th y squared on top of 2x6y6. So then simplifying the fraction first, 162 divided by 2 is 81. And then we'll use exponent rules to simplify our x's and y's. X to the 10th over x to the 6th, you subtract exponents so that we will get x to the 4th power. And then y squared on top and y6 on the bottom, that will give us a y4 in the denominator. Now we can simplify further by separating this into two separate radicals again. We'll have 81x to the 4th in the radicand in the numerator, and then y to the 4th, that looks like a 9, let me fix that. We'll have y to the 4th in the radicand of the denominator. So then in the top, we have the square root of 81x to the 4th. That will be 9x squared. And then down below, we have the square root of y to the 4th power, and that will just be y squared. All right, and that finishes up that example. The next part has to do with rationalizing a denominator. So we need a little background on that. Square roots of numbers that aren't perfect squares are irrational numbers. For example, the square root of 10, the square root of 19, and negative the square root of 11. The square roots of perfect squares do give rational numbers, but if we're taking the square root of something that's not a perfect square, we get an irrational number. What we're doing when we're rationalizing a denominator, rationalizing the denominator of a fraction, you're making a fraction that is equivalent to the given fraction, but that has a whole number in the denominator. The big idea is that when you see something like this 1 over square root 2, it's desirable, and we'll talk about why in a bit, to turn that into the square root 2 over 2. And how you do that is you multiply the numerator and denominator by the same value and change anything except for the looks. This pink fraction here, root 2 over 2, is 1. As you know, multiplying by 1 doesn't do anything. Here, though, it'll change the looks of it. 1 divided by square root 2 is the same as root 2 over 2. And that is the overall procedure right here, is you multiply the numerator and denominator by whatever that root is that sits in the bottom. And so before we go into trying it, I wanted to talk a little bit about why would you do such a thing? Because it doesn't look even like that much simpler than it was in the first place. There's two reasons for this. One is kind of artificial and the other one's kind of historical. So there's not really any good reason for it. One is so that everybody's answer looks the same. So if you're taking a class and doing all the work on paper and the teacher has to grade a whole bunch of these, then it's a lot easier if everybody has rationalized the denominator because then all the answers will look the same. Like I said, that's kind of a phony reason. And it's not, yeah, it's just kind of a phony reason. The other one is more historical. Now that we've had calculators for probably your whole life, but back in the days when there weren't calculators and people did math using tables printed in the back of the book, then and a lot of hand calculations, then it would be a lot easier if you've rationalized the denominator. For example, it turns out that the square root of 2 is about 1.4142, I think, and then a bunch more digits. Okay, and so if you needed to divide 1 by the square root of 2, and this is something that pops up in trigonometry a lot, if you needed to divide 1 by the square root of 2, then you would need to do this kind of long division problem. And nobody especially wants to do that. I know I don't. But if you've rationalized the denominator and now you're doing the square root of 2 for 2, 1.4142 divided by 2, that's a lot easier of a long division problem. Not that necessarily you would like it, but if you had to do it, probably you'd prefer to do this one more than this one. Let me go ahead and do that. This would give us 0.7071 or so. So a lot easier to do if the denominator's been rationalized. Like I said, now that you have a calculator that will do this kind of stuff, it's not really that exciting. But that's the reason why it was desirable. But it's part of our deal, so we are going to do rationalizing the denominator. Okay, so we want to simplify 4 over root 3. And how we'll do that is by multiplying the numerator and denominator by the square root of 3. Okay, if you do that, you will end up with on top 4 square roots of 3, and then down below root 3 times root 3 will give us 3. Next, we have negative 8 over 3 square roots of 6. Here, the 3 is not a problem, right? So I don't need to multiply the numerator and denominator by the 3. The only piece that is at issue is the square root of 6. So we're going to multiply the numerator and denominator by the square root of 6. So this will give us in the top negative 8 square roots of 6. And down below the root 6 will give us 6 times 3 is 18. Okay, so now you can see that we're going to need to simplify here. I'm going to divide out that common factor of 2. So we'll have negative 4 square roots of 6 over 9. You multiply the numerator and denominator by whatever that square root is in the denominator. Okay, and that's part of what it means or what you need in order to have a square root expression simplified, which is what we're talking about right now. A square root expression is considered simplified if there are no perfect squares in the radicand. So if you had something like the square root of 20, then that's not simplified because 4 is a perfect square. On the other hand, the square root of 21 is simplified because 21 doesn't have any perfect square factors. There are no fractions in the radicand, so you wouldn't want to see the square root of 3/4. On the other hand, if you had the square root of 3 over 2, then that is simplified. There are no square roots in the radicand. And then as we just discussed with the rationalizing bit, we don't want to see square roots in the denominator. So if you have 4 over the square root of 5, that wouldn't be considered simplified until you rationalize the denominator by multiplying numerator and denominator by the square root of 5 so that you get 4 root 5 on 5. So there's basically 3 criteria that you need to follow in order to determine that this thing is simplified. No perfect squares under the root sign, no fractions under the root sign, and no square roots under the fraction. All right, so let's try some more examples. Here we have 5 over 2 square roots of 5, and we're going to multiply the numerator and denominator by the square root of 5. Okay, so then up top we'll have 5 root 5. It's hard to draw square root signs in 5s. Root 5 times root 5 gives us a 5, times 2 makes 10. And then the 5 and 10 here have a common factor of 5, which can be divided out. Leaves us with the square root of 5 over 2. And that's the end of that. All right, so next we have the square root of 7 over 18. So I'm going to, there's a couple of different ways you can proceed with this. So if the steps you take don't match mine, that's fine. There's different ways of doing it. Here we'll have the square root of 7 over the square root of 18. And then I'm not going to multiply the top and bottom by the square root of 18 now, just because I don't feel like doing 7 times 18 very much. So instead, I'm going to simplify that square root of 18 first. So that we'll have the square root of 7 in the top, and then down below we'll have 3 root 2. That way, instead of multiplying the top and bottom by root 18, I could just multiply the top and bottom by the square root of 2. And that way I can keep the numbers a little smaller. We'll have the square root of 14 divided by 3 times 2, or 6. Okay, and that's it. So if you had chosen to multiply the top and bottom by root 18, then and then simplify, you would end up with the same answer. Okay. Here we have the square root of 10 over 50. So I think all of us here are going to just simplify the 10/50ths first and make that 1/5. And now we can multiply the numerator. Well, let me separate this into two fractions or two radicals first. Root 1 over root 5. Now we'll multiply the numerator and denominator by root 5 so that we get the square root of 5 over 5. Okay. All right, so that's basically how you deal with it if the denominator is a single term. Our last topic for this section is what do you do if the denominator has two terms in it? So that's here. In order to do that, we use the difference of squares formula, also known as the conjugate binomial formula. So remember that a plus b times a minus b is the same as a squared minus b squared. When you multiply these two binomials together, you end up with just the a squared and just the b squared. Notice that there's no a's or b's. So if a and b have roots in them, they end up squared, and that eliminates the square root sign. Let's see an example just with multiplication. If we have 2 minus root 3 times 2 plus root 3, using this pattern, we would have the a, which is 2 here, squared, minus the b, which is square root of 3 squared. If you want to use FOIL or something, go ahead. But if you follow the pattern, it's faster. 2 squared is 4. The square root of 3 squared is 3. You end up with 4 minus 3, or just 1. Okay, and that's it. Notice that there's no roots left behind. If you were to do like FOIL on this, you'll notice that the outers and inners cancel, and those are the ones that contain the square root. And that's the basis for how rationalizing the denominator with two terms is going to work. So let's try it on this one. We'll have 5 over 5 plus root 3. So let's multiply the numerator and denominator by the conjugate of the denominator. So that's going to be 5 minus root 3. That's 5. All right. So then up top, I'll hold off on the multiplication. Let's just write it out. 5 times 5 minus root 3. I'll do that in a minute. Maybe I'll get lucky at the end and something will cancel that 5 out. So I'm just going to leave it factored for right now. Okay, so then down below, we'll proceed kind of like the example we just did a second ago. We have 5 times 5. That will give 25. The outers and inners cancel. And then in the back, we have root 3 squared, which is a 3. So there isn't any simplification. That's going to give us a 22. So we'll have 25 minus 5 root 3, and that is over 22. All right, and that is it. Notice our denominator doesn't have any roots in it anymore. This is kind of a weird simplify process because usually when you simplify stuff in math, it gets like smaller and better looking. This, to me, it looks almost worse. I mean, there's still 3 kind of terms in there. It's still got a fraction bar, still has a root in it. It's just we've moved the root around. So that can be a little off-putting for people, but that's the way it goes. At least the denominator doesn't have any square roots in it anymore. Okay, so let's try this one more time. Here we have 3 over 1 minus root 5. And remember that it is always the conjugate of the denominator. Last time, in the last example, it was 5 plus root 3. So in red, I have 5 minus root 3. This time it is a minus in the first place, so we'll make it a plus. So we'll have 1 plus the square root of 5. A common mistake is just to square the denominator or to multiply by just the root 5. And if you try those, you'll see that they just don't work. All right, so then multiplying across, 3 times 1 will be 3, plus the 3 root 5. And then down below, 1 times 1 is 1. And then minus root 5 times root 5 is just a 5. Okay, so then we'll have 3 plus 3 root 5 divided by negative 4. And then I think it looks nice just to bring the negative out front of that one. Negative 3 plus 3 root 5 over positive 4. Okay, all right. We have just 2 more examples to do, and then we're all done with it. So let's see how that's going to look. These have some variables in it. That's not going to change how we do things, though. Here we've got 5 over root x plus root 2. What is different, aside from the variable, is the fact that there's 2 square roots in the denominator now. Before, we just had a root 5 and a root 3. Now we have actually 2 square roots, but it's going to be all right. We'll multiply by root x minus root 2. That's a little thick. Root x minus root 2. All right, so then let's see what we get. So 5 root x minus 5 root 2. Then down below, root x times root x will give us x. And then again, the outers and inners will go away. We'll have minus 2 down below. Yes. And we're all done. Again, it doesn't end up really any simpler looking, but technically it is because there's no roots in the denominator. All right, here's one for you to try. Pause the video, try this one yourself, and then the video and see how you did. All right, so here you would multiply the numerator and denominator by square root of x plus the square root of 3. Make sure that you're multiplying the numerator and denominator by the same thing. You have to make sure that you do that, otherwise the value changes, right? You don't want that. All right, so then up top, we'll have root x. This is a perfect square trinomial. You can use that formula if you want to. We'll have root x times root x, which is x. And then root 3 root x, root 3 root x. So that's 2 root 3x's. And then in the back, there's going to be root 3 squared, which is just a 3. Okay, down below, we'll have root x, which is a solid x, minus 3. Okay, and that's it. So we succeeded in rationalizing the denominator. And that takes us to the end of this section on dividing involving roots. Let me know if you have any questions, and have a great day.